So I want to begin our discussion in electrochemistry by reviewing oxidation numbers. There are a few simple rules that you're going to follow for assigning these oxidation numbers, and you'll do them over and over. And you will see one or two questions like this on your final exam. And this will directly lead into our discussion on electrochemistry. So if we were to consider the simple polyatomic ion permanganate, MnO4 minus, the overriding and controlling rule is going to be oxygen is almost always -2. It will be 0 if it's in the context of its standard state element, which is O2. It will be -1 if it is in the context of a peroxide like H2O2. So we know that oxygen is -2, and there are 4 of these. So all of the oxygens together has a charge of -8. I don't know what manganese is. I'm going to represent that as X. And I know that the overall charge of the ion is -1, and just a simple algebraic step shows us that manganese has an oxidation state of +7, an oxidation number of +7. And you'll need to be able to do that for a question or two on your final examination. So let me give you a couple of examples. Let's look at OF2. Let's look at H2O2. Let's look at NaClO4. So with OF2, oxygen's going to be -2, which means each fluorine will have to be +1 to make it a neutral molecule. In H2O2, each hydrogen is +1, each oxygen is -1. Of course, in sodium is going to be +1 always. Each oxygen is -2, which means chlorine in this case has to be +7. You will find lots of other examples in chapter 19 of your text. And there were probably other examples from your first semester course that you can also look at. So you need to be able to assign oxidation states. Now we can start talking about electrochemistry. In electrochemistry, we are going to have a series of reactions which are going to transfer electrons. So literally you have 2 cells, or if we were to use the simplified notation, imagine 2 different beakers in the laboratory in which I have 2 different metal electrodes. And I'm going to use the classic example of the zinc-copper electrode. So I will have zinc a very thin plate of metallic zinc in one of my beakers that's immersed in a solution. And the solution would be something like zinc sulfate. And in the other beaker, I'm going to have copper. So this solution is copper sulfate, while this solution is zinc sulfate. They're going to be connected through a wire that will be attached to a voltmeter. This is simply going to measure the transfer of electrons by measuring its voltage. Also, there will be a device that we call a salt bridge. And the purpose of the salt bridge is to prevent a buildup of charge. And for this system, let's just say that our salt bridge is comprised of potassium nitrate. Usually what you do is you get like a U-tube and you fill it with a potassium nitrate impregnated agar solution so it actually solidifies, so then you can turn it upside down and put it into the solution. Now, one of these cells is going to be capable of chemical oxidation. And one's going to be capable of chemical reduction. In other words, one of the beakers will have a half reaction, that is oxidation. One of the beakers will have a half reaction, that is reduction. So let's take a closer look at this. And to do this, I want to go ahead and redraw this picture and look at each beaker individually. So in this classic example, copper is going to be produced when copper ion, that same copper ion that was a part of the copper sulfate solution, gains 2 electrons to become reduced to copper metal. It is reduced because the oxidation number of copper 2 plus decreases or is reduced from +2 to 0. So this is called chemical reduction. Lots of ways of remembering chemical reduction. One of the most famous is Leo the lion says Gur. I know it's kind of lame, but it works. Loss of electrons is oxidation. Gain of electrons is reduction. So electrons will be a chemical reactant in the reduction half reaction. They will be a product in the oxidation half reaction. Furthermore, there's another mnemonic, red cat. That reduction will always take place at the cathode. And this is the cell that we're talking about with reduction. We're talking about the cathode. And we have this half reaction that is occurring. Now let's take a look at what's going to happen at the anode. So we want to look at our zinc cell. So in our zinc cell, we're going to have oxidation. And as this reaction proceeds in this half cell, the size of this electrode, this thin plate of zinc, is actually going to decrease. Zinc will be converted to zinc 2 plus 2 electrons. Notice this is oxidation. And our electrons are a product. This is called the anode. One nice way of remembering that the anode is where oxidation occurs and the cathode is where reduction occurs is that anode and oxidation both begin with vowels, whereas cathode and reduction both begin with consonants. Again, it's a lame mnemonic, but it may or may not work for you, so if it does, go ahead and use it. If it doesn't, forget we ever had this conversation. So now what we want to do is let's put this all together in the context of a reaction, because the anode half reaction cannot occur without being coupled to the cathode half reaction. So everything has to work in concert here. Zinc to zinc 2 plus. Of course, this will connect to my voltmeter. Copper 2 plus goes to copper. Of course, these are immersed in an aqueous solution. And of course, we have a salt bridge. Now we're going to talk about the role of the salt bridge momentarily. And remember, we have K plus and we have NO3 minus. You should very quickly realize that unless we have a mechanism to prevent the building up of charge, which of course would immediately prevent a current from continuing to flow in the circuit, and it's the flow of electricity that's really relevant in electrochemistry. Either we are going to use a spontaneous reaction to produce a current, or we're going to use a current to make a normally non-spontaneous reaction to become spontaneous. So I would build up positive charge in the anode and I would build up negative charge in the cathode. The negative charge that I would build up would result from the sulfate that I have in solution and the disappearance of copper ion. So over time, the size of the copper cathode is going to get bigger as more copper 2 plus becomes deposited as copper metal. And the size of the zinc electrode is going to shrivel. And the mass that I lose in zinc is going to be equal to the mass that I gain in copper, of course. Law of conservation of mass. So we're going to build up a positive charge here. To offset that, the negative charge in the salt bridge, the nitrate ion, will migrate and to pair itself with the developing charge of zinc 2 plus. Notice the anode is where the anion migrates. In fact, it's called the anion because it migrates to the anode. Conversely, K plus is going to migrate to begin to replace the Cu2 plus that's being lost out of solution. It is the cation that migrates to the cathode. In fact, it's called a cation because it migrates to the cathode. Now, you might remember that it was a cathode ray tube that led to the discovery of the electron. Before the cation, migrates to the cathode is negatively charged. Just like before the anion migrates to the anode is positively charged. So do what you need to do in order for those terms to make sense to you. Now, the electrons are lost from the anode and gained at the cathode. Therefore, in this kind of cell, called a galvanic cell, sometimes also called a voltaic cell, and these are just named in honor of the two Italian physicists who did much of the initial work of establishing electrochemistry as a science, Galvani and Volta. In fact, the word volt is also in honor of Volta. Both of these terms indicate an electrochemical cell that is spontaneous, of course, we know if it's spontaneous, then the delta G of the reaction is less than 0. And in this type of cell, the electrons will always move from the anode to the cathode. Electrons move from the anode to the cathode. There is another type of cell that we'll talk about shortly called an electrolytic cell. In an electrolytic cell, you still have oxidation at the anode, you still have reduction at the cathode, but you have a battery that supplies a current. And that battery will deliver electrons in the opposite direction. So in an electrolytic cell, the electrons will move from the cathode to the anode because of the presence of a battery. Now, we will have a typical voltage for each system that we subject to a reaction. For example, this is a very classic example, and the total voltage is 1.10 volts. Let's look for a moment at how we get those numbers, how we do this math, because we're going to relate the electrical potential, which is E, standard state, to delta G. So in a spontaneous cell, a galvanic cell, or a voltaic cell, E has to be positive, whereas in an electrolytic cell, E will be negative. So let's take a look at that. So we want to look at something called reduction potentials. The only data that's absolutely provided are data regarding reduction potential. So for example, zinc 2 plus 2 electrons yields zinc metal. This has a reduction potential of negative 0.76 volts. In our reaction, we were doing the exact opposite. We were oxidizing zinc. So what we would need to do would be to flip the equation around and change the sign with our reduction potential, and now we make it an oxidative potential. The other half reaction is fine just the way that it is, because copper 2 plus indeed was reduced to copper. and it has a reduction potential of plus 0.34 volts. So we flip equation 1 and flip the sign and then add them together and you get 1.10 volts. The more positive a reduction potential is, the more positive a reduction potential, the more easily that species, and of course that species is going to be the reactant, is reduced. So there's a hierarchy. When I have reduction potentials of a species and it's more positive than another, that means that that species with the more positive reduction potential is more easily reduced. Just as a very quick example, copper ion is more easily reduced than zinc ion. Compounds that are easily reduced make excellent oxidizing agents. Now this is where a lot of people begin to get confused with electrochemistry. So let me walk you through the logic. If I am a species that is easily reduced, I easily gain electrons, which means I easily accept electrons from a source that's losing them. And the source that's losing them is itself becoming oxidized. So a reducing agent is itself oxidized, while an oxidizing agent is itself reduced. So oxidizing agents are reduced. Reducing agents are oxidized. And to really grasp this, you have got to see the holistic picture that a half reaction is not a reaction in and of itself. If I am able to reduce a species, that species is gaining electrons from something else that's losing electrons. Oxidizing agents are reduced and reducing agents are oxidized. So let's talk for a minute about balancing some redox equations that aren't as easy as our model system. So I have chosen to show you an oxidation half reaction where aluminum metal is oxidized to aluminum 3+. And of course, since it's been oxidized, it's lost 3 electrons. Permanganate can be reduced to Mn2+. So it goes from +7 to +2. And that is going to be through the gain of 5 electrons. So notice that when we balance chemical reactions, we not only have to balance the number and type of atom, which is kind of drilled into you in Gen Chem 1, we also have to balance the charge. Let me say that again. To balance an equation, to balance a chemical equation, You must balance the number and type of atom. You must balance the total charge. And when I say total charge, that means the charge of all of the reactants has to equal the charge of all of the products. For example, in this oxidation half reaction, the charge of all the reactants is 0. The charge of all the products is 0. In the reduction half reaction, the charge of all of the reactants is plus 2. The charge of all of the products is plus 2. I have 8 hydrogens, 8 hydrogens. I have 1 manganese and 1 manganese. I have 4 oxygens and 4 oxygens. When this is done, I can begin to look at how I would add these two equations together to write a balanced chemical reaction. But the problem is I don't have the same number of electrons that are transferred in the oxidation half reaction as compared to the reduction half reaction. So what I simply need to do is find the least common multiple. Least common multiple of 3 and 5 is going to be 15. I want to multiply the top equation by 5, and then I want to multiply the bottom equation by 3. When I do this, so I'm going to go ahead and erase my definition. So if we do some simple math, we have 5Al plus 24H plus 15 electrons plus 3 permanganate yields 5Al 3 plus 15 electrons plus 12 H2O plus 3 Mn2 plus. Now, of course, electrons never occur in the stoichiometry, so the 15 electrons in reactants and products cancel. We have 5 aluminums on both sides. We have 24 hydrogens on both sides. We have 3 manganese on both sides. We have 12 oxygens on both sides. So the number and type of atom is fine. Charge, I have plus 24, plus 21, plus 15, plus 21. This is now a balanced equation. I have balanced both the number and type of atom, and I have also balanced the charge. So if you were to receive an equation like this and you were to be asked how many electrons are transferred, the answer is not 3, even though it's 3 for the oxidation half reaction. The answer is not 5, even though it's 5 for the reduction half reaction. The answer is the least common multiple of those two numbers. The answer in this case would be 15. So I think I want to stop this podcast, and I'm going to pick up with another one where I cover the other topics on electrochemistry that you'll need to know for your final examination. And of course, we can talk about this in class later today.